Before leaving this problem and leaving this result, though, I'd like to consider an interesting piece of physics. There's something a little troubling to me about this reflection probability. I want you to notice something. If I look at this probability of reflection, right, it's basically the momentum difference over the momentum sum squared. And once again, I can turn it exactly into that by multiplying the top and bottom through by h bar. And when I do that, what I end up with, you will notice, h bar k2, right, is just now literally the difference in the momenta divided by the sum of the momenta squared. But what puzzles me about that is that that expression, when I write it this way, makes no reference whatsoever to h bar. Right? There's no reference to quantum mechanics in here at all. This is just a simple, classical looking formula. And if I think about a macroscopic particle, because there's now no h bar in here to make things small, that means I should expect some kind of a reflection for a classical particle. And that's quite puzzling. Suppose I took a classical particle, right? And I know how to make a potential step, right? I could literally take a physical step, and I could take something like a ball, right? And I could let it just roll over this step, and I could ask, well, what type of behavior would I be expecting? And I could certainly design it so that when the ball goes over the step, say it doubles its velocity, just for sake of argument. Well, so we can just suppose, and this is not hard to set up, but suppose we set things up so that the momentum P2 is twice momentum 1, right? And the funny thing then is that because there's no h bars in here, when I substitute in, that would mean then, under my little supposition here, I would get something like P1 minus twice P1 over P1 plus twice P1 quantity squared, which would give me the P1's cancel, and I'll have a minus 1 on top and a 3 on the bottom. So I would have 1/9, or about 10% chance of being reflected. So what we're saying is, if I take a macroscopic ball, right, so it's a macroscopic ball, and I roll it over a little ledge like this with, this quite natural choice of speeds, right? It should, when I keep doing this, 1 out of every 10 times, I should see that ball just turn around and come right back at me. That is what we are predicting here. And that is pretty puzzling because you can do the experiment. It's not going to ever come back. But there's no h bar in here to take to 0, right? There's something seems to be wrong. We spent all of this time building this beautiful formal theory, and in one of our first new predictions, the whole thing has just fallen flat on its face. Something appears to be wrong here, right? The quantum is very clear that I should get some significant amount of reflection in this case, but we are not seeing it. So there's a little bit of an apparent paradox. Now, the way to resolve that paradox, though, is to go back and ask yourself what it is in quantum mechanics that makes us think that there should have been this reflection. What makes this a significant reflection? And we had said it traces back to the wave nature in quantum mechanics. So our resolution here will have something to do with the wave nature of our ball. Now, the idea behind the wave nature and the reflection was that whenever any kind of wave hits a sudden change in potential, or I should say a sudden change in propagation properties, there will be a reflection. But when we say we have a potential step with a sudden change, we have to really specify sudden compared to what. So when a wave hits a sudden change, sudden has to mean sudden compared to the wavelength of the incoming wave. If the step is sharper than the incoming wave, then yes, indeed, we expect a reflection. If it's not a sharp transition, but some kind of a smooth transition, waves don't reflect from smooth changes in the propagation media. So the question really is, how does my step size compare to the incoming wavelength? We want to consider then the de Broglie wavelength. Now the de Broglie wavelength for something, as you know, is Planck's constant divided by the momentum. Now, if I'm dealing with macroscopic numbers, right, I'm just dealing now with rough order of magnitudes, right? H has a rough order of magnitude of about 10 to the minus 34, right? The momentum of some macroscopic particle, it might be a heavy ball, maybe a cannonball, right, would be about 1 in SI units. So then my total magnitude should be about 10 to the minus 34th meters, order of magnitude. Maybe it's 10 to the minus, 30, not 10 to the minus 34, but it'll be something on that very small order. That means I have to make a step in potential when I do my experiments that is sharper than this tiny distance. But I want you to remember that the size of an atom is about 10 to the minus 10 meters. My de Broglie wavelength is 10 to the 24th times smaller even than the size of an atom. Now, if I do this as a macroscopic experiment, it's very hard to imagine that I could actually design a lens, a step. Even a good carpenter would have trouble making a step that is sharp and well-defined down to the last row of atoms. And even if such a carpenter could do that, right, what still we have is over that transition region of 1 atom, which would be the best we could imagine doing, the de Broglie wavelength of my macroscopic particle is so tiny it will have 10 to the 24th oscillations as I go over that transition region. If I were to sketch what the potential looks like compared to my waves, so here's my waves, right? They look like this. And my potential starts here at its value. In order to get far enough out over here, right, that my value has made it down to 0, right, or down to the lower level, I would have to go 10 to the 24th of these waves. So on this scale, this transition looks incredibly smooth. So there really wouldn't be any reason for there to be a reflection generated. The failure in our calculation wasn't anything wrong in the quantum mechanics we did. The failure actually is trying to model a potential as a discontinuous step when I'm dealing with a macroscopic object. We just physically can't make those. If we were dealing instead with electrons, then indeed we can get to situations where there is a sudden change in their potential. This kind of thing happens, for example, inside of certain semiconductor devices. And then this type of calculation actually gives quite accurate results. But for macroscopic objects, we have to be careful how we model things. Very good. So that really then completes what I wanted to say about this simple type of an example.